Thank you for joining in. This project is funded by the European Union Horizon program. Our webinar series Lessons Learned is a part of the Circuits project and contribute to the dissemination of our 3 years innovation action results. Please enjoy.
Okay, so today I'm going to present the results related to the automated PCB disassembly task that we developed during the project. As Paolo briefly mentioned at the beginning, this was not, let's say, initial planned activities for the project, but in the end we managed to work side by side with pilot leaders and provide some interesting results in this scope. So I would like to start giving a brief context of what we did and why. So as we may know, the semiconductor sales, especially in the automotive sectors, has been rising through the last years. And if we look at projections, this rising is supposed to continue in the next years. And this exposes us to several possible risks and several possible areas where we can improve what we are actually doing. In fact, electronics devices, especially the ones included in automotive these days, are pretty rich of critical raw materials. And we know that current end-of-life management is pretty inefficient from these regards. In addition, only from a point of view of the materials, there is also the fact that some of the components are destroyed with the board, even if they are maybe still functional. So, as briefly said, this is going to expose the supply chain to possible risks, mainly related to critical raw materials increased pressure. And the way that we wanted to address this problem is to try to create a sustainable process to disassemble and reuse only key components, because we are well aware that disassembly is always adding cost to the processing of the material. And to do so, we wanted to explore what could be done with an automated approach instead of a manual disassembly and slow approach to the disassembly of these components. To this end, we developed, let's say, 3 different key technologies inside the project that has been then used in the 2 use cases that we will see in a while. The first one is based on the localization capabilities of components on the printed circuit board. So we developed an AI tool that is capable of localize integrated circuits, in particular on the board. And then we use a sort of pipeline of algorithms to not only detect integrated circuits, but also to identify the specific integrated circuit that we want to disassemble. This technology has been coupled with robotic disassembly techniques. So after we are able to identify this kind of component, we can then guide the robot to disassemble those components. A lot of work has also been done in terms of robotic end effector, because we wanted to create end effectors capable of disassembling in a non-destructive way components from printed circuit board. And lastly, the latest technology that we implemented in this case is automated optical inspection, especially for what regards flexible electronics after the disassembly process. In fact, we wanted to assess the health status of flexible electronics after the disassembly in order to allow in an automated way repairing actions. So I'll start from the first use case. The first use case is focused on automotive ECU disassembly, in particular on braking units ECUs. As you can see, in this slide, we will see mostly the approach that we had to adopt in order to solve these issues, because one of the most critical point in this activity was the fact that even if we would be able to disassemble the component in a non-destructive way, we would not be able to test the functionality of the component afterwards. This has several reasons why. One of the most important is that when we are working on ECU, and especially safety ECUs like braking units ECU, most of the times the components are encrypted. So in order to prevent any possible modifications to the component, it's not possible to directly access to the component. So to overcome this problem, we had to create this closed loop approach with the OEMs. In this particular case, we worked in contact with Bosch, who was the OEMs of the ECU control unit. The workflow is pretty simple in some way, even if it consists of several, let's say, closed loops. The first part of the work starts with the targeted identification, proceeding with the manual disassembly test following IPC standards. After the manual disassembly test, the components are sent back to the OEMs in order to test them, and then it starts the prototyping and design of the automated solution, starting with the localization and manipulation capabilities, so machine vision and effector prototyping, and passing to the full automated procedure. Afterwards, all the components are once again tested by the OEMs in order to validate the whole procedure. I will show you some videos and some more detailed information, let's say visual information, in the not public part of the presentation. But basically, what we managed to achieve is that we automated the disassembly of one specific components on Bosch ECUs without damages. So we had the validation from Bosch that the procedure works. We developed what you can see here in these images, that is a new kind of end effector capable of desoldering galwing components from printed circuit board. You can see that basically we are using thermal pliers that are encapsulated inside to the parallel finger gripper. So of course this is a low TRL prototype, but it was still functional for the task that we had to do. For what regards the second use case, we were focusing, as briefly said before, on automated optical inspection for disassembled flexible electronics. Basically, going a little bit more in detail on what happened to these samples, after the injection molding of the flexible electronics and the manual disassemble of these electronics, we may encounter some of the defects that have been reported by TNO in this sort of catalog of defects. The most impacting ones were the ones related to missing LEDs that may have been removed during the disassemble procedure. And in addition to that, the shift of the coordinates of the components. This mainly due to the fact that when the sample is injection molded, it undergoes a sort of heat treatment that may deform the original shape of the original layout and the original shape of the sample. And this is quite critical because these components on the board were really small, in the order of idea of half of a centimeter big. And the manual inspection would be really time-consuming and also, and due to that, could be quite expensive. So the focus was to be able to assess the health status of these samples before going to the repairing process without having to spend a lot of time by manually doing so. In this regards, we used cutting-edge technology coming from the market. In this case, mostly we worked on smart cameras, so with advanced computer vision capabilities. We worked with 2D laser profilometry in order to have 3D laser profilometry in order to reconstruct 3D data of the sample, and we also we also designed, because unfortunately we weren't able to fully test this solution, a telecentric system capable of measuring the coordinates on the sump. So at the end of this activity, we managed to demonstrate that it's feasible to have an automated assessment on the health status of the PCB. And this can be done, as said, by combining different technologies. We can see here in some of the images the setups that we used in several scenarios. As said, I will show more in details in the not public part of the presentation. We have on the left the laser profilometry that, as you can see from the, let's say, colored images, allow us to create a topography of the board, easily identifying where the component is missing. And then on the right, we can see the approaches used with telecentric objectives and smart cameras in order to assess the presence of defects. So, what are the key innovations that we embedded in this activity? First of all, the AI-driven vision. So we managed to identify successfully, by combining different approaches, the desired components that we want to disassemble. As you will see in the last part of the presentation, we not only used classical AI using convolutional neural networks, but we also made some testing using optical character reading, which is a quite old technology, but still really reliable. And we also tried some approaches with the visual language model in order to see how these new models can ease the task that we were trying to achieve. Then we developed an adaptive robotic tools that allows us to precisely remove electronic components without damaging them. And in the end, we assess feasibility for automated quality inspection of flexible electronics. So as said before, this was not let's say, planned activities at the beginning of the project, and we didn't know if we would be successful in what we were doing, because as said, it was it is, as you can see, also a really low TRL activity. The point is that we, at the end, had pretty good results. The feedbacks also from the partner were pretty good. And so we started also to work not only in a technical direction, but we wanted to work also in the direction of trying to improve this kind of solution. And one of the ways that we thought about doing so is to try to create a spin-off company of Polytechnic of Milan that will be dealing with this kind of technology developed. And in order to do so, we had to start making sort of analysis on how we could do so. So starting from the market value and impact potential, it's pretty obvious by what we said at the beginning that the growing demand of electronic components, and in particular of the most valuable components, it could expose in some way supply chains to some sort of risk. And so being able to mitigate this kind of risk could be really important in the next years. The competitive advantages in this sense are mostly due to the fact that, to our knowledge, up to now, there are no other solution that allows to be able to non-destructively disassemble components in order to reuse them. And in addition to that, inside our team, there is also a strong know-how on critical raw materials risk analysis. So not only we could develop and own the technologies for the disassembling and remanufacturing of critical components, but we can also assist companies in understanding what are the, let's say, most relevant components to be disassembled. As you could see from the previous slide, in addition, this approach is modular, so the scalability is quite easily obtainable. In terms of instead of economic and societal impact, we could assure reduced production cost, especially if this solution are embedded in production lines, where we could directly work on production waste to reintroduce components inside the production loop. In terms of environmental benefits, of course, we could lower emissions related to the manufacturing of new components and consequently reduce the extraction of critical raw materials. For what regards our idea for an industrialization roadmap, this is what we thought could be feasible, because as I said before, this is still a pretty low TRL technology. And so the idea is to have for the next year a consolidation of the prototype that we developed, reaching TRL 5.6. Then in 2027 we could try to implement the pilot line in real production conditions. In 2028 the idea is to reach TRL 8.9 by trying to extend this practice to multi-component and multi-product handling. And lastly, in 2029, go to market deployment and expansion in order to actually be present on the market. The idea, of course, is to leverage a new European project in order to be able to develop this kind of solution. Of course, we are well aware of the risk that we may encounter in this journey, mainly due to the fact that, as we know, there is a little bit of resistance from companies in order to remanufacture electronics. Let's say that up to now the most used way to see this problem is to, if the electronics is broken, to throw it away and build a new one. So there is also, let's say, a sort of cultural barriers that we have to overcome. Of course, even if we are well aware of this, we know that we can adopt some mitigation actions. The context of European project where we can directly work with OEM, where we can co-design solution is one of the best places where we can also in some way demonstrate that we are effective in what we are doing. So, as said, we would like to transform what is up to now a circular vision into an industrial realities. We will do this in several ways. As said, we will leverage new calls of the European projects, and we hope that we will be able to bring our solution to reality.
Thank you for watching this webinar episode. If you're as passionate about sustainability and innovation as we are, here's how you can get involved. Stay connected with us on our social media and website for the latest updates and insights from the Circuits project. Whether you're an individual or an organization, there are plenty of ways to contribute. Reach out to us to learn more about partnership opportunities, events, and initiatives.